Welcome back to the series on statistics. In this video, I'm going to be solving some normal distribution problems. I'm putting off making this video for a while now because I think this kind of content is somewhat dull. So far in the series, we've derived the probability density function, the cumulative distribution function, the moment generating function, and all sorts of attributes about the normal distribution. So we know everything we would want to know about it for at least an undergraduate level. And we have this property here that we've established based off of that information, which is that if we have a normally distributed random variable, let's call it x, with a mean of mu and a variance of sigma squared, then we know that the probability of that random variable taking on a value between the interval from a to b is just going to be equal to the integral of the probability density function on the interval from a to b for the general normal distribution. And so that's this expression right here. The idea here is that this is very verbose, and if you wanted to solve several of these probabilities in sequence, you could imagine you would get very exhausted writing out all of these different things into Desmos over and over and over again. And so there must be a quicker way of doing this. There is a quicker way of doing this. If you wanted, you could just imagine programming a function that's just this, but you take as argument the mean here, the standard deviation, and maybe the bounds of the integral, or maybe just the top bound. And you could imagine if you wrote that program, then it would be a lot faster. And indeed, that's exactly what modern day calculators have done. So if you use a TI-84, there's the normal CDF function, which stands for the normal distribution cumulative distribution function. This one takes as argument the lower bound of the integral, the upper bound, the mean, and the standard deviation of your distribution. And you can find this under the distribution category, or the dist category. This is second vars on your calculator. If you're using R, you have the comparable equation, or comparable formula, which is going to be P norm, but this one only takes as argument the upper bound of the integral. And so the lower bound on this one is always going to be negative infinity. And the reason this is not an issue is because if you want to calculate the integral from a to b of the probability density function, giving you the cumulative distribution function, you could calculate this just as easily with this P norm function, just by, let's say the lower bound here is always negative infinity. And so if you want negative infinity to b of I'll just write CDF for simplicity, this minus the integral from negative infinity to a of the CDF dt, these two integrals are exactly equal. This is just from the properties of calculus. And so you really only need to define the upper integral here in your function, and that's why R only defines the upper value of the integral, because this is just as easy as this. But it's a little bit convenient. If you're using a TI-84, it's a little bit easier, I think, to use their CDF. And so I primarily use the TI-84 to compute these probabilities. You also have another function on your calculator or in R, and these are going to be the inverse norm or Q norm functions respectively, depending on what software you're using, or I guess hardware. These functions here are going to give you the z-score equivalent to a particular probability. And so I have a little example here. You know that if 50% of the area under a standard normal curve lies to the left of the mean, and we know that the mean is 0, then the inverse norm of 50% or 0.5 is going to give you 0. It's just going to give you the z-score, right, that corresponds with a particular percentage. And so another example of that would be, we know from the empirical rule, this is most easily understood with a picture. We know from the empirical rule that if you have a normal curve here, which is, this is a terrible one, but let's just add some values here. If you have sigma here, negative sigma, and the mean here, then we know that 64% of the data lies between these two bounds here, lies within one standard deviation of the mean, or 68% of the data. And so if 68% of the data lies between these two means, then what would be the z-score that corresponds with one standard deviation away? What would be the z-score that would correspond with this value right here? That would be, what would the probability here be? You would have 50% plus 34%, so this would be 84%. And so if you did inverse norm of 0.84, then you would get this value here, which is just one standard deviation away from the mean, and one standard deviation away from the mean would give you a z-score of 1. So if you plug this into your calculator, you should get something very close to 1. And so I hope that makes sense. These are the two functions we're going to be using. We're not going to use inverse norm as much in this video. So if this doesn't make too much sense, don't worry about it. We'll talk about that more when we talk about confidence intervals and hypothesis testing, because that's going to be more important there. But the key idea here is just that these normal CDF and p-norm functions are a lot easier to use, easier to solve with, than writing out this entire expression. However, these functions here are literally just this expression. It's just all being handled by your calculator instead of you having to write everything out. So this just makes things easier for us. With that said, let's look at a couple example problems and just reinforce our knowledge, make sure we know what we're doing with all of this. All right, so this is the first problem I have here. All of these problems I pulled from the Math Stack Exchange. This one says that Wink Inc. is made up of 450 employees who work a total of 13,500 hours per week. It says that the number of weekly work hours per person has a normal distribution, and the standard deviation is 7 hours. How many employees work more than 37 hours per week? Okay, so we have lots of the information here. We have the bound on our integral, we have the standard deviation. The only thing that we're missing is the mean, and then we can use the probability density function, or the cumulative distribution function for the normal distribution to compute the probability of working more than 37 hours a week. And then you can multiply that probability by the number of employees to get the expected value, or the approximate number of employees who work more than 37 hours per week. And so that's the procedure we want to follow, but we are missing the mean of this normal distribution. However, we're given the total hours worked per week, and we're given the total number of employees. And so I would argue that it makes sense that the average number of hours worked is going to be the total number of hours worked divided by the number of employees. And so this will be the mean of our average weekly hours per person, and this is going to equal 30. And so now we have all the information because we have that our standard deviation is 7, and we're asked to compute the probability that a given person works more than 37 hours per week. And so I'll say that the hours worked is greater than 37. And you have a couple different options of computing this. You could do normal CDF on your TI-84. And this one allows you to enter several different values for your integral. And so you could literally just do 37 all the way up to infinity to get the probability of your hours worked being greater than 37. If you want to do infinity or negative infinity in your calculator, the easy way to do that is just do 1e, or I was used to writing these capital E's backwards. You want to do 1e99, and this will give you 1 times 10 to the 99th power. If you want to do negative infinity, then this would just be negative 1 to the 99. And so that's how you can enter that into your calculator if you want that bound on your integral. And so then we have these bounds on our integral. Now we just need to put in the mean and the standard deviation. The mean here is 30, standard deviation is 7. This will give you the probability. Alternatively, if you don't want to use this as your upper bound, you could just use the fact that the total area under the curve is equal to 1, and then you could just subtract off the probability of working less than 37 hours per week, and this would be 1 minus the normal CDF from negative infinity now up to 37. So it'll encompass all the values less than 37 with the same mean and standard deviation. All of these should give you the same answer. You could use R to do this as well, so you could use that. But the other way you could do this is you could recognize that this is the standard deviation, and we're asked the probability of the hours worked being greater than 37. And so we can actually use the empirical rule here, since this is quite cleanly just 1 standard deviation above the norm. I think I conveniently have described this in the beginning of this video, but if you look at 1 standard deviation within the mean, we know that this area is going to give us 68%, or 0.68. And so the area that lies above the mean, but is within 1 standard deviation, or the area within a positive 1 standard deviation of the mean, this is going to be 0.34. And this area right here, everything to the left of the mean, is going to be 0.5. And so everything underneath this 1 standard deviation away from the mean here is going to be 0.84, the sum of these two areas. And so if we want everything above that, if we were instead interested in this area, this would just be, this area would just be 1 minus that area. And if we compute that, we'll get about 0.16. And so I would argue that all of these are acceptable answers. and they should all get you these two should give you exactly the same thing if you plug them into your calculator, and they should be both pretty close to 16%. And if we know that roughly 16% of the employees work more than 37 hours per week, and we know that 450 employees work there, then we could say that roughly the amount of employees that work more than 37 hours per week would be 16% multiplied by 450, and this will give us a total of 72 employees. And so this is the approximate answer here. I think if you do this probability with the normal distribution, I think the rounding will give you 71, but these are just fine. We're approximating here, and so these would be acceptable answers. And so this should be the approximate number of employees who do work more than 37 hours per week. All right, here's the second question here. He says that this is one of his homework assignments. The weekly demand for a product has approximately a normal distribution with a mean of 1,000 and a standard deviation of 200. And the current on-hand inventory is 2,200, and no deliveries will be occurring in the next 2 weeks. Assuming that demands in different weeks are independent, then A, what is the probability that the demand in each of the next 2 weeks is less than 1,100? And B, what is the probability that the total of the demands in the next 2 weeks exceeds 2,200? And the student informs us that he does not even know where to begin. Okay, so let's see if we can figure this out. For the first question here, what's the probability that the demand in each of the next 2 weeks is less than 1,100? This doesn't seem too hard. We're given a normal distribution for each week. And so we know that the normal distribution has a mean of 1,000 and a standard deviation of 200. And so if we want the probability of the demand being less than 1,100, this is just a normal CDF. And then we want all of the values to the left, all the values that are less than 1,100. So this is going to be from negative infinity. Really have to think when I'm writing that capital E. And we're going up to 1,100. And here we have a mean of 1,000 and a standard deviation of 200. And so this will give us the probability of the demand in each of the next 2 weeks being less than 1,100. And if you plug this into your calculator, you should get about 0.69. And so there's about a 69% chance that the demand in each of the next 2 weeks will not exceed 1,100. And because the demands in these 2 weeks are independent, we can also say that the probability of the demand in each of the next, like both of the next 2 weeks, doesn't exceed 1,100. We could just say that this is equal to the product of this and itself, since they have the same probability of being less than 1,100 and they're independent. We could just multiply these probabilities together, and the probability of, let's say, week 1 being less than 1,100, probability of demand in week 1 being less than 1,100, and the probability of the demand in week 2 being less than 1,100. This is just equal to 0.69 times 0.69. And if you plug that into your calculator, you'll get about a 48% chance. And so I'm not exactly sure what the question is asking here, because it says demand in each of the next 2 weeks, so I don't know if that means the demand in both of the next 2 weeks being less than 1,100, or if it's asking us what the probability is that in one of the next 2 weeks that the demand will be less than 1,100. So I just went ahead and solved both of those problems here. The next part of this question asks us about the probability that the total of the demands in the next 2 weeks does not exceed 2,200. And so here we're dealing, you could think of the demand in each of these weeks as a random variable. Both of these random variables are identically distributed. They're both normally distributed with a mean of 1,000 and a standard deviation of 200. And they're independent because that's given to us in the question. And so we can treat these as independent, identically distributed random variables. And we can add them up. And so the mean of the sum of these two random variables, say big W1 plus big W2, this is going to be normally distributed. And the mean here will just be the sum of the means of both of those distributions. And so that's going to be 2,000. And the variance here, if the variance is the sum of the squared deviations away from the mean, and we wanted to sum the squared deviations away from the mean for the sum of those two variables, you could think that the sum of the squared deviations away from the mean for this random variable is just going to equal 200 squared. That's the variance. And for this variable, it was also going to equal 200 squared. And so if we were going to add these two variables together, we would just add the sums of those standard deviations away from the mean, or the sum of the deviations away from the mean squared for both of these random variables. And so in other words, we would just sum the variance. And so the variance here would just be 200 squared. Remember that this 200 is the standard deviation, not the variance. But for the sum of these two random variables, it's going to be the sum of both of those variances. And so this gives us a new normal distribution with a mean of 2,000 and a standard deviation of the square root of 2 times 200 squared. And if you plug this into your calculator, looks like you'll get about 282.84. And so now, if we want the probability of the demand in week 1 plus the demand in week 2 being, exceeding, so being greater than 2,200, I'm going to do this way. This is just 1 minus the probability of the sum of the two demands being less than 2,200. And if you wanted to write that in your calculator, you could write that as, I just need to do it this way to make space, but this is just normal CDF. And you would go from negative infinity, I think that's the right way, and then this would go up to 2,200, since we're subtracting this off of 1. And then now we would have a mean of 2,000 and a standard deviation of 282.84, looks like. And if you plug this all in, it looks like you'll get a probability of, 0.24. And so that's our answer for part B. Now there's a key thing here to point out. In the first question here, we computed the probability that the demand does not exceed the threshold that we're looking for here. So, like for example, if the demand was 1,100 in both weeks, we would run out of stock. And so here we computed the probability that in each week, or in both weeks, that the demand did not exceed 1,100. And we got the probability of the demand not exceeding being 0.48, which tells us the probability of the demand exceeding 1,100 would be 0.52, or 52%. Now here, this is much different from what we got when we computed the exact same thing, this is in quotes here, according to summing up these random variables. And so why is this number so much bigger? Why is this probability so much higher than this one? I encourage you to pause the video and think about that because it's a little bit nuanced, and it will definitely get you thinking like a statistician, because it's very easy to fall into different pitfalls here and say, well, these two events are independent, so we could just take the product to compute the probability of the demand being exceeded or not. But if you do that, you will actually get the wrong answer, and this is the correct answer. And so why is this answer incorrect? Why does that not give you the probability of demand being exceeded? Right, so hopefully you paused the video and gave that a little bit of thought, because I consider this to be a little bit important. The key here is that this condition here is too strict of a requirement versus this, which is exactly the requirement we want to see what is the probability of running out of stock. The reason this is too strict is because we're asking what the probability is that in both weeks we don't exceed this half of the stock that we have on hand. But that is not the necessary condition that tells us whether or not we will run out of stock. Yes, if this happens, if the demand is less than 1,100 in both weeks, then we won't run out of stock. But there's other situations that are not captured by this probability statement where we don't run out of stock. For example, imagine the demand in the first week is 0, then this condition will be satisfied, but the demand in the second week was like 1,500, 1,900, 1,600, something like that. Then we would have enough supply to satisfy the demand of both weeks. That condition would be satisfied, so this would be true, but this statement would be false because the demand in week 2 would exceed the threshold that we've outlined here. So this is actually too strict of a requirement, and so you would expect that this probability is less than what it would need to do to give you the right answer. And so if this probability was a little bit greater, then this one would be a little bit smaller, and it would tend towards this one, which gives us the answer that we're actually after, which is what's the probability of running out of stock. I hope that makes sense. that's something that's important to consider. So if that didn't make sense, I'd imagine I would encourage you to think about that a little bit. It's important to understand these types of nuances. All right, with that being said, this is the last problem I have here. The question says that the time spent studying by students the week before exams follows a normal distribution with standard deviation of 8 hours. A random sample of 4 students was taken in order to estimate the, I guess it's supposed to be the mean study time for the population of all students. And we're asked what the probability is that the sample mean exceeds the population mean by more than 2 hours. And so we should already be familiar with the sampling distribution, or the distribution of sampled means. And so just a little bit of a review. If we have our distribution of sampled means here, this is always going to tend towards a normal distribution as your sample size grows bigger and bigger and bigger. But here we're given in the question that the time spent studying by students the week before exams follows a normal distribution. And so that tells us that the population is normally distributed already. And so we actually don't need the condition of a large sample size, since each of these samples is going to mirror the population distribution. If the population distribution is normal, then our sampling distribution is going to be normal as well. But that being said, the sampling distribution is going to have a mean that's equal to the population mean, and a standard deviation. The standard deviation of our distribution of sampled means here is going to equal the standard deviation of the population divided by the square root of the sample size. And so we should already be familiar with these facts. If you're not, I encourage you to watch my video on the distribution of sampled means, or the sampling distribution. Now here, we actually have this information given to us in the question. We're told that the population has a standard deviation of 8 hours, and that the sample size that we're dealing with is 4. And so this tells us that the standard deviation of our distribution of sampled means is equal to 4. And so what this is asking us is, if this is the distribution of sampled means, and let's say that this is equal to 4 right here, so this is 1 standard deviation away from the mean, this would be then 2, and we're asked what the probability is that x bar will be in this little area here. And so what this would be equal to, this would be the normal CDF, here from 2 to infinity, and then we would go from the population mean, and we'd have a standard deviation here of 4. Now here, we don't have enough information to solve for this probability in this way, but we can use as our friend the z-score, and because we already know that this is true, that if x is a normally distributed random variable with a mean of mu and a variance of sigma squared, we know that if this is true, then z will be a normally distributed random variable with a mean of 0 and a standard deviation of 1. If z, I guess I should say something else because of that if that I wrote up there. So this is given z is equal to x minus mu over sigma. And if we compute this property right here, or the number of standard deviations away from the mean that something is, that's exactly what this is. You're subtracting the difference between x and your mean and dividing by the standard deviation. So this is telling you the number of standard deviations away from the mean that a given outcome is. If we can compute this information, then we could just solve this normal CDF, but we could use a mean of 0 and a standard deviation of 1. So this would solve our problem here of not having enough information. And so we're asked what is the probability that the sample mean exceeds the population mean by more than 2 hours. And so this is the probability of the z-score being higher than 1/2, because this is half of a standard deviation. And the probability of the z-score being higher than 1/2 is just going to be from a standard normal distribution, the normal CDF from 1/2 up to infinity with a mean here now of 0 and a standard deviation of 1. And if you plug this into your calculator, you'll get about 31%. And so it seems to be that the probability of the sample mean exceeding the population mean by more than 2 hours is about 31%. I hope that was useful. Hope that made sense. I hope this gives you a good few examples on how to solve these problems a little bit more efficiently than having to plug all the information into these giant integrals every time you want to compute one of these probabilities. Thank you guys for watching, and I hope you all enjoyed.